haven't looked at the ones yet that came in afternoon on Monday, like the ones that came in near midnight. Somebody had it at 11:59, and I haven't graded those. So if you want to know how you've done, if I've graded it, your grade is should be available to you on SmartSight. And I'll try and get the others in the next 2 days. I think I should be finished them all by Thursday. But there were at least 6 of them that came in after I stopped grading, and then I was busy doing other things. So just keep checking SmartSight, and when I've done it, it'll be there. Because as soon as I grade it, I'm entering it onto there. I'm just waiting till my watch says it's 10 after. Okay, are we ready? Okay, so I changed my mind about proving Chebyshev's inequality, since I'm going to try and prove something else today instead. And I just try and say what it's good for. So we have this integral, and we can estimate it by choosing some probability density, either uniform or, as I'll talk today, maybe non-uniform will even be better. And estimate the integral by taking n samples and averaging the value of f of xi over p of xi. And that's what I call the estimate I of n. And what you can get out of Chebyshev's inequality is, suppose you know how close you want to get. You can't guarantee you'll always be that close, because if you pick random samples, you can always get a fluke. But based on the variance of this function f of x, or the function fi over pi, you can choose n big enough so that the chances of getting a worse error than the error you specified is arbitrarily small, as small as some other number. So you can pick these 2 numbers, and then if you look at the formula in the book for the Chebyshev's inequality, it shows you can guarantee that this will be true if you take n big enough, and the formula for n is going to use the variance. Obviously, if the variance is big, then you need a larger n. Okay, so instead today I want to talk about sampling random variables. And I'll start by a finite case. So suppose there are n, do I want lowercase or uppercase n? I don't care. Say lowercase n possible outcomes of the experiment. Say, so we have probabilities pi for I equals 1 to n, such that the sum I equals 1 to n, I equals 1 to n of pi is equal to 1, and the pi's are greater than or equal to 0. So I'm back to the discrete case. I'm going to do that first. So, for example, suppose all you had was a random number generator, like the one I use is drand 48. But I did read this morning that article in the IEEE Spectrum. They're a way to build circuits out of transistors, which will also generate random bits just by amplifying the thermal noise. You set a sort of a flip-flop so that it starts in the middle, and it could fall equally likely in either way, just based on the thermal noise on the chip. And you get a collection of random bits there, and you sort of sanitize them by using them as seeds for another random number generator. And you end up with, physically random numbers. But you could also get it. This is just a bunch of arithmetic that gives you a random number between 0 and 1. So if you had that, say a random number u, so DRAN gives, if I take u equals DRAN, then 0 less than or equal to u less than 1, and it's uniformly distributed in this interval, equal probabilities for any u. But now we want to get unequal probabilities, basically. Like suppose we wanted to simulate an unfair coin. Or say unfair die, because then we have 6 possibilities. And suppose it was, here were the numbers, 1, 2, 3, 4, 5, 6. Let me make up some numbers. 0.1, 0.1, 0.1, 0.2. What have I got? I've got 5.3, 0.2. So suppose those were the numbers I wanted to give. Those, if I've done this right, 3 and 2 is 5, and 3 and 2. There's that up to 1. So how could I use this random number u to generate these numbers with these probabilities for these cases? Well, I'll tell you how. Let's make a graph here. Maybe I'll put it on this board. I'll put it down here. So here is, let me start it at 1, 2, 3, 4, 5, 6. And I'm going to make a bar graph here where this height is 0.1, that height is 0.1, that height is 0.1, this height is 0.2, this height is 0.3, and this height is 0.2. And then I'm going to add these up. So on this next graph, let's make a break here. Here's another graph. I'm going to make basically the cumulative distribution here. I'm going to start this one, I guess here is 0. And now it goes up to 0.1. Now I'm going to add the other 0.1 to this, so I get it up to 0.2. And I'm going to add another 0.1 to here, so it gets up to 0.3. Then I'm going to add another 0.2 to that, a bigger hunk here. And I guess to the next one I want to add 0.3. And then another 0.2. And now we're all the way up to 1. Right? So these heights are 0.1, 0.1, 0.2, 0.1, 0.2, 0.3, 0.2. Okay, and so the total height at the top is 1. And on the base, I'm going 1, 2, 3, 4, 5, 6. So the trick is, this is like the cumulative distribution. Now I pick a random number uniformly between 0 and 1 here, and I just see over which bump it hits. Right? Well, since these heights are equal to those probabilities, that means if this number is random, then the height will be, the chance of bumping onto this height is proportional to the height here, right? Because we're just picking a random number which is uniformly distributed here. So the fraction that hits each height is equal to that height. So basically, what we're doing is saying this function CDF of I is the sum j equals 1. Let's see if it stops at I or I minus 1. I think it stops at I of the probability of I. Either P sub I or I can write it P of I. Right? And then that means the probability of I is equal to CDF of I minus CDF of I minus 1. Right? And that's exactly this height here. And that's why it works. So I want to do the same thing now for continuous distributions. Say, on the interval AB. Don't remember whether the book did it on AB or not, but let's just take a distribution that's defined between A and B and is some probability density, like that. Here is P of x. And then the cumulative distribution function of x, this is P of x, is basically CDF of x is equal to the integral of a to x of P of t dt, right? It's the integral up to x. And what that is the probability that t is less than or equal to x, right? If you pick a random t according to this distribution, this integral is the chances that it will get up to x, right? For a continuous distribution, you integrate that density over an interval to get the probability of that interval. Here it's the probability of the interval from a to x. So here the slope is slow. When I get larger up to this value, the slope is steeper. Here it's steepest up here, and then it sort of levels off. And eventually when we get up to b, it has value 1. Okay, so basically, if you pick a number u, then come over here and find out CDF inverse of u. That's basically what we're doing, right? If we take a function, we take a value here and see what the CDF is. If we take a point here on this axis and go over and then down, we're taking the inverse function. And this is a 9 decreasing function. Right, so that this doesn't bump back down, we're always going to get a well-defined inverse. And, well, I guess if the probability were ever 0 here, right, then our curve would be like flat for a region. But that's okay if we have a little flat region here corresponding to this place where it was exactly 0. Then we're never going to end up bumping into there, right? You may say the inverse is not well defined, but really it's supposed to represent probability 0 in this interval. So you could count it like at this point if it hit here, and you would never count these points. So just as it works here, you can prove mathematically the density of points is proportional to the slope, right? If you have a steep slope, then if you have a certain collection of equally spaced points, there are going to be more here. And if you have a small slope, then equally spaced points are going to be more separate here. Or like here, these points are quite separate because the slope is low, because that's the region. I guess I'm not exactly aligned correctly. This should have been up at the end here where the slope was low. I don't think I got my eyeball doing the A and B exactly correct, but it's what I meant to do. Okay, and the book has a proof based on this fact that says that then you have the right probability distribution just by looking at the slope of this density gives you the probability density, the slope of the cumulative distribution, because the cumulative distribution is the integral, right? So its derivative is back to that density. And that's giving you the probability of actually along this u-axis. I mean, let's say this is the x-axis, and this is the CDF axis. So it's analogous to this case, and there's a proof in the book that it works. So that's fine if you can do this integral analytically. And we'll get an example later on in the class where you can do the integral analytically. But there's another method. If all you have is the function, maybe you get it by evaluating by a subroutine, and the subroutine involves ray tracing or something. It's not something you could ever integrate analytically. Then there's another way to do it, which is called rejection sampling. And that is if the probability of x is always less than or equal to some number m. You have a maximum bound on your density function. Then what you do is you think of, here's a plot of the density function. Here, I'll again make it between a and b. And I'll make it go between here, 0, and m. And my graph then, if I look at this box here between here, 0 and m and y and a, b, and x, I know that my probability density is entirely inside this box. Actually, let me make it so it actually comes close to m. Okay, so suppose I generate two random numbers. Let say it should be uniformly distributed in A and B. How can I do that using this random number u? What can I do to DRAND 48, which will give me a number between 0 and 1, to make it go between A and B? Well, when this DRAND number comes to be 0, I want to have A. And when DRAND is 1, I want to have B. So I just have to multiply it like this. B minus A, which is the width of the interval, times this. Right? So basically my probability density is 1 over B minus A, because it integrates to 1 over B minus A. And then let's take number u, which is uniformly distributed between 0 and m. It's just m times another call to the whatever source of random numbers you've got. So now we have some random point in this rectangle. In the book there's a picture of a lot of them. What we want to do is choose only the ones that are inside this curve. Right? Then the marginal distribution of, what did I call this one? T will actually be this probability, right? Because if we integrate, if we accept only the points inside here and reject those, then the probability of accepting the point is proportional to the height of this curve. So the way to write the code, do I have a code here? I don't know. I can still write the code here because I don't think I've got it, at least on the page of the notes I'm looking at, is to just say if, how do I want to say this? U is less than or equal to PT except T. T is the x value you want here. And I can make a while loop out of it. In other words, keep doing this until you get one that's accepted. Right? Then you'll only accept the ones that are under the curve, and so the probability of any x is going to be proportional to the height of this curve here. But you can see, first of all, you need two random numbers instead of one, and second of all, you need perhaps, in this case, looks like this area is even bigger than that area, or maybe it's the same. You need twice as many points as you're eventually going to get x values, so it's 4 times as much work in this case. So it's better if you have something you can actually compute this analytically and actually get its inverse function. So I want to show an application of this kind of integration, which is the integration that we wanted. Well, let's see. Let me introduce it first, because that's the way I introduce it abstractly, and then I'll apply it to what we're doing in this course. Variance reduction methods. Right? What we had is sigma squared for n samples is 1 over n times sigma for one sample. That's what I proved last time. And when I wrote this Chebyshev inequality that I erased, I said if n is big enough, you can make this get small. But it depends on how much the variance is for one sample. You know how big n you have to make. So it's better if this variance to begin with is small. And then to get the same error, you'll actually need fewer samples. And so to integrate what I've suggested before, integral from a to b of f of x dx, we could choose p of x equals a constant. And what would that constant have to be? If it integrates to 1, and it's a constant, integral k from a to b dx is b minus a times k, and that's 1, so that constant has to be 1 over b minus a. And so if it's 1 over b minus a, then our estimate for one of them, I'll call it number 1, is just f of a sample xi, which is generated between a and b by like the kind of formula I wrote on the far board for my, what was it called? I guess that's the t. And then divided by b minus a, and that's my estimate for one integral. But I don't have to use uniform probability. I'm going to draw a picture of an f. Here's my a and b, and here is some f. If I take b minus a, 1 over b minus a, this is p of x, and this is f of x. It turns out that I can make the variance of fx over p of x smaller by finding a case where here is my a and b, and I'm going to try and draw approximately the same curve here. Meant to be the same, but I'm not a great artist, so I didn't succeed in making it the same. Something like that. Suppose I made, say, something like a piece of a parabola here. Or maybe a piece of a cubic curve that actually has more of a hump on one side, is sort of asymmetrical here. So that the ratio of f of x to p of x didn't change that much. But p of x was something that I could integrate easily and get a cumulative distribution for. And therefore estimate, get a random sample that's proportional to p of x. Well, if you look at the variance, if what you're doing is thinking about integrating f of x over p of x times p of x dx, if the variance of the thing you're integrating is smaller, then your sigma 1 here, the variance, this should have been squared. Sigma 1 squared is going to be smaller, right? Because this f of x over p of x is differing from the average value less, if that ratio is pretty close to the average value of f of x over p of x. So even if you can't get this exactly, it helps to get it close. And the book proves that if you could make f exactly proportional to p, you've got the minimized variance. In fact, that variance is 0, right? Because if we take p of x is some constant times f of x, to keep that ratio constant, then what we need to know is that the integral from a to b of p of x dx, that would have to be 1. And that's the same as taking the integral from 0 from a to b of f of x dx times k. So that's k times the integral. So k has to be 1 over this true integral. And then what does that mean? Then p of x is f of x over the integral. And then the estimate, I1, is the integral of f of x over p of x times p of x dx, which is, how can I say that? No, it's, let's see if I did this right. Because I've got an extra p of x here. Oh, no, the sigma squared. That's what I want. This is the integral. My sample, my estimate of I is just f of x over p of x. And the variance is the integral from a to b of the difference between f of x over p of x and the true integral squared dx. This is going to be f of x divided by f of x over I, and that this is the turn, if you turn the fraction over, this is just going to be I, and I minus I is 0, so your variance is 0. And the reason is because every sample, this is the first sample you take, it's f of x1 divided by f of x1 over I, that's just I. Well, something's fishy here. How can you get something for nothing? The problem is we can't do this because we can't find k because we don't know the I. I is the thing we're trying to find. So that means we can never make this variance 0. But by making the p of x non-uniform so as to more closely approximate f of x, we can make the variance go down. And so let me do this now on the application that we actually want. So suppose we're trying to estimate the reflected radiance. I'm just going to write the equation from the book that I've been writing on the board before. X reflecting in direction theta is the integral, let's do the hemisphere version, of the bidirectional reflection function. Here's an incoming direction reflecting to this theta. And then we have the light coming into x from that direction, psi. And then we have cosine nx psi d omega psi. And this says we're trying to integrate over the hemisphere. So we can make our estimate by picking a random direction on the hemisphere. And then what we have to do is evaluate these three numbers at that direction, divide by the probability of getting that direction, which is basically 1 over the area of the hemisphere, and we'll get an estimate. But if we know one of these distributions, and we can integrate it analytically, there's a product of three numbers. If we can at least cancel one of the numbers by our probability, we'll get something that varies less. And the obvious thing to do is to cancel this one. This one says, basically because of the irradiance factor, the cosine of the angle, here is the normal, nx. Say here is a piece of surface here. And here is a hemisphere above that point on the surface. And what we want is a random unit vector psi in that hemisphere. And what we're going to do is we're going to sample the light in that direction, say by tracing a ray to hit the other surface, whatever it hits, and then multiply that by the BRDF. In fact, what I'm eventually going to assume is the BRDF could also be constant. If it was a diffuse surface, this wouldn't be vary. And then it's difficult to estimate according to this direction because until you trace the ray and see what it hits, you don't know. But this one, you could estimate because this is an analytic thing. So what we want to do is make P, the probability of sampling in any given direction, proportional to cosine of theta, where theta is the angle between this direction and the normal, right? We can think of two directions. We can think of x-axis here. We can project this down and get this phi, which is the azimuthal angle. These are the two components of the spherical coordinates now. And basically, what we need to, in order to make the integral of over the hemisphere of x of p of psi d omega psi equals 1, what we can do is say 1 equals, let's integrate between 0 and 2 pi d psi, d phi, and the integral from 0 to pi halves d theta of cosine theta. Okay, we did this integral before. It's just the area of the hemisphere, which was 2 pi. No, let's see. This integral. No, it came out pi. I remember now. It's not the area of the hemisphere anymore because it's a cosine-weighted hemisphere. This is what we did when we did Lambert's law, because we were trying to find a similar factor in the Lambert's law to conserve energy. So that means k, if this is going to be k times this integral, then is the probability. I forgot this factor k. It's got to be pi, then k equals 1 over pi. Okay, so that means that what we want to do is sample according to this cumulative distribution function. In other words, here is theta going from, cosine theta going from 0 to pi halves. Did I write pi halves there? Yeah. And if we take 1 over pi times it, 1 over pi cosine theta, and now we want to make the cumulative distribution of that. I guess here it's increasing fast and here it's increasing slowly. Right? That's what we want to use to sample it. So basically, we're going to sample phi uniformly. between 0 and 2 pi. So we can take phi is 2 pi times this random number generator. But what do we have to do with cosine theta? Basically, what we have to say is that if we're forming the cumulative distribution when theta starts from 0 and goes down to pi halves, it's really the distribution, it's the area of this cap of the sphere up to pi halves that we have to do, because it's really a two-dimensional, two parameters. It's the, if we have theta up to a certain direction, we're actually, to get the cumulative distribution, we have to integrate from the top of the sphere down to a certain level. Let me pick the level of this great circle here that came through this angle theta. We have a certain spherical cap here. It's similar to the integral that we did to get this pi here. What we have to say is the cumulative distribution function of theta is the integral from 0 to 2 pi d phi times the integral from 0 up to theta of, say, cosine t dt, and we had a 1 over pi here because we had 1 over pi cosine theta. So this part of the integral, this doesn't depend on phi, and so this is going to be 2 pi, and cancel the 1 pi. We'll get twice the integral from 0 to theta of cosine t dt. And if we think about cosine, this is actually, if we take minus cosine squared t, and I forgot, this is wrong now, because it was supposed to be cosine theta, sine theta, d theta, right? This d omega is d theta d phi times sine theta. Because we're going to integrate up to theta, we're going to integrate all the solid angle in this cap up to angle theta. And so I forgot the sine theta part of the d omega. And so this is cosine t sine t dt. And now this is the derivative with respect to t of this thing, right? Because cosine, the derivative of cosine is minus the sine. That'll cancel this minus sign. And because of cosine squared, we have 2 times cosine t times sine times the derivative of what's inside, which is minus sine t. And this cancels the minus, and the 2 cancels the 2. Right? So this derivative equals that. And so this integral is these 2's cancel, and we have minus cosine squared t evaluated between 0 and theta. So at the lower limit, we subtract. So let me do it properly. At the upper limit, it's minus cosine squared t, and at the lower limit, it's a minus 1, and then so it's subtracting minus 1 is plus 1. So we can say minus cosine squared t plus 1 equals CDF of theta. This was theta, right, at the upper limit. And so if I'm going to take, let's see. So I want to find theta so that the cumulative distribution function is a random number u between 0 and 1. Right? Because that's, if I can solve this equation for theta, then I'm going to compute the CDF inverse of u to be the theta that makes this be true. And so what this says is that cosine squared theta equals 1 minus u, bringing this to the other side and the u to this side. And so theta equals the square root of cosine inverse of 1 minus u. See if that agrees with my notes. I have cosine inverse of the square root of 1 minus u because it wasn't cosine theta squared. It was the fact that cosine theta squared was u. So cosine theta is this. Basically, it was really, this is what I meant, right? So I did that wrong. So this means that cosine theta equals the square root of 1 minus u, and theta equals cosine inverse of the square root of 1 minus u. Now, it turns out that u is, if u is uniformly distributed between 0 and 1, so is 1 minus u. So you don't even have to do the subtraction. You could just take another random number and take theta equals cosine inverse. What's that? In C, I think it's arc cosine, a cosine. I don't know how to spell it. Of square root of rand, d rand 48. Something like that. That'll get you the phi and the theta, and then you can pick a unit vector using the spherical coordinates in that direction. And that'll give you a sample, and that will be better than sampling uniformly because we made it proportional to cosine theta. If we were sampling uniformly, then this cosine factor would go out, and we just have this sign to integrate, and we wouldn't get the squared thing anymore. Right? So we would avoid this square root. We'd be sampling uniformly, but in terms of getting reduced variance, we're better to sample non-uniformly because the light contributing from the surface coming on angles that are more directly above instead of tangential is actually going to contribute more to the integral. So it's better to make more samples there. That's the philosophy. So another thing we might want to do is do jittered sampling, which the book calls stratified sampling. And one application of that is to do anti-aliasing. If you have a geometric scene and you just do ray tracing like you did for the homework, you'll see your spheres have jagged edges, right? Because the ray either hits it or it doesn't. But suppose you have a single pixel, and here's the square here, and you make multiple samples inside here and take the average color. Then you're going to get an average color, which is going to be some mixture of the background color and the color of the sphere. And so you won't get the jagged edges. Instead, you'll get some sort of shade of gray. Or, you know, if this was white and that was black or something, you get some mixture of the colors. But it could happen by the random number generator that all your samples happen to be clumped over here. And then you'd incorrectly get the color of the sphere. And so if one way of reducing the variance of the integral is to try and prevent them from being clumped. And the jittered sample method says, suppose you divide this region into, say, 5 by 5 horizontally and vertically subsquares. And you pick 25 samples. One sample is uniformly distributed in this one sample uniformly distributed, that means in X and Y, in each of these subsample locations. You know, I'm just picking random points here. I'm not aiming at the center. I'm just... Well, you're never going to get them all clumped here because there's some squares out here that need them be. Have one samples in it. So that's going to involve less variance. And I was going to give a proof that the variance decreases I think what I'll do is I'll try and start it, and I may have to continue it next time. So let's look at just the one-dimensional case because it works equally well there. So again, we're trying to estimate I equals the integral of f of x dx. Say, let's go from 0 to 1. That's the way they do it in the book. And let's assume we don't know anything about f. We can't use this non-uniform probability. We'll just take a uniform probability. So we're just going to estimate it by I1, say, well, no, it's this IN is the sum j equals 1 to n, capital N, I guess, should be f of xj. Right? There's no, if the probability is uniform between 0 and 1, that means the probability density for each xj is 1. So there's no p anywhere or not even any constant. And now we'll take the interval, and the way we'll get the xj is we'll divide the interval up into n equal parts, and we'll pick a random xj in the jth piece. I should have drawn them dots right on this line, somewhere on this line, so that we know that xj is between alpha j less than or equal to xj less than alpha j plus 1, where in our case alpha j equals j over n. Right? Those are our n boundaries, 0, 1 over n, 2 over n, and so on. So what can we say about the variance knowing we put these xj's in these specific intervals, somewhere randomly, uniformly distributed in each interval? Okay, the expectation of this IN, the expectation of the IN is the expectation of, should have been 1 over n times this sum. Let me write it separately. The expectation of this estimate, it's still true that this expectation, even though we didn't choose them each one randomly in the whole interval, it's still true that we get the same answer. Because this is equal to 1 over n times the expected value of this sum, f of xi, and the expected value of each of these is the same as an integral. One to n of the integral from alpha I to alpha, let's see, alpha I minus 1 to alpha I. That's the ith interval of f of x over the probability of x. And the probability is uniform, right? But in each interval here, this interval has width 1 over n. So if the integral of a constant integrated over an interval of width 1 over n is that constant over n. So that constant over n, which is the integral of a constant between alpha I minus 1 and alpha I dx, because the alpha I minus alpha I minus 1 is 1 over n. If that's 1, what that says is k equals n. So really this is 1 over n times the sum I equals 1 to n of the integral from alpha I minus 1 to alpha I of f of x dx. Well, this sum is just as if you integrated over the whole thing, right? If we take the sum of the integrals over each little piece, this becomes the integral from 0 to 1 of f of x dx. And the n cancels that n, the 1 over n cancels that n. So even though each of these wasn't distributed over the whole interval, we still get this expectation as the same as before. But we want to make the variance less. And I can see by my watch I'm not going to have time to do that. So, well, let's see. I may do it next time. I maybe save it to the end of next time. And if I have time after what else I have to talk about according to the syllabus, I'll give you the proof. But intuitively, I explain why it should be less variance. So I'll try and make time to give the proof tomorrow. I mean Friday, whenever the next class is. But I have to stop now. But that's the idea of jittered sampling.